the single track wall, for instance. So we are very limited in the area of direct heat dissipation, and we have also a lot of like heat losses, maybe not a lot of heat losses, but we have heat losses to the powder, which some investigations show that they are between 3 to 5% of the conduction of that material. So how the sample size affect the microstructure? Okay, doesn't work. Well, in order to answer this question, I have chosen Hastelloy X as a base material because it's very commonly used for aerospace industry or power plant sector, and it's simple alloys, so it's solution strengthened, which is characterized by very good processability, in contrast to, for instance, precipitation hardened nickel alloys, which are really susceptible for cracking. So in the first stage, I have optimized the parameters based on the simple cubes to get almost like fully dense part, like nearly 100%. And in the second stage, I have printed set of different samples, different thin walls. But what is important here, I want to just really track what is happening with the microstructure track by track. Because very often what we observe in the literature, people are just showing 0.200 micrometer, 400 micrometer, 600 micrometer, but we do not really know what is happening even on a melt pool scale, like how different melt pools affect each other. So looking at the cross sections and the melt pool, or in general, the morphology, so we can see that 1 track and 2 tracks, they are like least stable in terms of the geometrical accuracy. The surface, like the quality, improve with the number of tracks, or actually stabilize from the 3 tracks, and all the thicker walls, they are more or less equalized. Luckily, we didn't see any defects, so that means that we can transfer the parameters from the simple geometry to the thin walls. But we can see that we have a lot of changes in the melt pool geometries, especially between 1, 2, and 3 tracks. Starting from the three tracks, the microstructure is, or the melt pool formation, melt pool morphology is more or less equal. So in the 1 track wall, we can observe that we have wider and shallower melt pools, and also we have the second, like the area is sort of like a time from going from the main melt pool. And on 2 tracks, we have relatively shallower melt pools, but still they are slightly deeper than in the 1 track sample. And starting from the 3 track sample, the melt pool are entering almost like a transition or nearly keyhole mode. But what is also important to note that on the side, each melt pool that is in a direct exposure to the powder, to the sides, to the surface of the wall, it's way shallower, and it's sort of like a flattened towards the surface. If you will take a look at the solidification cells, in a 1 track sample, we can distinguish these 2 areas that I have mentioned before, that we have 1 melt pool consisting of the 2 areas, and we have the 1 area which consists of very, very fine solidification cells. I checked the primary tender arm spacing, and it shows that this is around 3.6 times 10 to the power of 6 Kelvin per second, while on the upper area where we have coarser solidification cells, the solidification rate was around 10 to the power of 5. If we will take a look at the thicker samples, so we can observe that we have slightly finer solidification cells, whereas only when you fabricate subsequent melt pools, so when we are just overlapping the melt pool with the previous one, we can see area with the coarser solidification cells. But in general, in the rest of the melt pool, the solidification cells are finer in contrast to the one-track sample. Moreover, we can, starting from the three-track sample, we can observe very elongated epitaxially growing solidification cells that are just oriented parallel to the build direction. Moreover, what I mentioned also before, on the melt pool scale, we had a big difference near the edges of the sample. The solidification cells near the edges are larger. This mostly, it can be mostly explained by the limited heat dissipation and heat loss to the powder. So how to explain the formation of this melt pool in a single track wall or multiple tracks? So when we are creating the melt pool, we are just dealing with the denudation of the process. Simply, we have a lot of evaporation of the material, which decrease the pressure inside of the melt pool, and we have later on direct sucking of the powder to the melt pool. And what is happening? And it leads to simply creation of like some voids or empty spaces. And over the time, we have also impact of the gravitational forces that are acting on the edges of the melt pool. But at the same time, on the bottom, on the central part of the melt pool, we have already solidification. So this part solidifies while the upper parts start collapsing, and we have a lot of liquids on the top. In the multiple tracks, we have very similar effect near the edges, and we have also the nudation of the process, and gravitational forces are acting on the wings of the melt pool. And that is the reason why we have this flattened melt pool towards the surface. Looking at the EBSD graphs, there is also a significant difference, like before 1-2 track samples, and from the 3-track samples, more or less we start stabilize for the EBSD, the texture is more or less orientation of the grains is more or less equal. It's like purely polycrystalline material. In the one, for example, we have extremely fine grains that are just growing towards the center of the wall, while on the 2-track sample, they are sort of like inclined 45 degrees towards the left side. What is also worth to note that we have on the samples that consist of 3 tracks and more, we have these thin stripes of 100 direction. So this is what I have mentioned before about the solidification cells that we could observe in the center of the melt pools, or elongated solidification cells, which appear to be here as well. And on the sides of the wall, we can also observe relatively smaller grains, which can be explained that also the solidification is oscillated on the powder that was lying near the edges of the sample. So when we have the collapse of the melt pool, we have still some powder directly lying in the vicinity of the melt pool, and we have solidification. Looking at the invert plots figures, we could not observe any difference here. I mean, we could observe the difference, but we couldn't see any strong texture in neither of the sample. Only in the 4-track sample, we have more pronounced texture in the direction, in this 01 direction. However, I have checked also like 5-track samples, 6, 7, 8, and they didn't show this effect. So I can imagine that also it is correlated, and it can be also random when we change the area of the investigated sample. So in order just to track the thermal history, what is happening in the sample, so we simply done test using the thermocouple. So we printed like the base plate with some channels where we applied and attached the thermocouple, and we have printed different thin walls on top of it. And on the right-hand side, we can see the graph that we have typical thermal history of laser powder bed fusion consisting of rapid preheating, rapid heating, and rapid cooling. However, what is very important now is that we do not observe any preheating effect. Very often people are referring that we have global preheating during the laser powder bed fusion. However, when we are just dealing with it, small thin walls samples, we are reaching slightly above 50 Celsius degree, which is not really significant, and this effect is vanished after 150 layers about. So this work, this thermocouple test has been also applied to calibrate our thermal simulations. Will you be able to play these videos, all of them? No, the videos.
The number?
All of them. 3 and 4 track.
3 and 6. 2?
Yeah, 3 and 6. So as we can see here, so the single track is pretty simple. We are just scanning everything close down. On the 2-track sample, so we are also do not have such a any preheating effect when we are just scanning the 2nd track, because the local preheating is reaching only around 100 Celsius degree. But the difference starts from the 3-track samples. So when we start scanning the 3rd track, for instance, in this case, so the local preheating in the area of 3 layers underneath reaches 400 Celsius degree. And this effect is even more enhanced when we are printing thicker samples. So this is also, out of it we can explain that we are just entering this deeper metals in the thicker walls, because we have local preheating that affects also the recoil pressure, and we are simply creating this transition mode for nearly keyhole. So just to summarize it, so the largest differences we could observe on the geometry is between 1 to 3. Above that, the microstructure and is sort of stabilizing. We could observe finer solidification cells in the thicker samples, and on a grain size in the 1-track sample was characterized by finer grains in contrast to the thicker samples. No texture were observed in the all samples, and we could observe small local preheating while we are printing thicker ones. Okay, thank you very much for your attention.